Okay, so this is the second video where we're going through this paper here, which contains some higher tier material. Okay, so it says a Welsh company has been asked to design a toy that is able to launch a model plastic plane. They decide to use a spring mechanism in its design. Initially, they carry out an experiment to investigate whether a spring is suitable for use in the toy. Slotted masses are added to exert a force on the spring. The resulting length of the spring is measured. The results are shown in the table below. So we've got the mass, we've got the equivalent force, and then we've got the length of the spring that causes. Okay, so it says plot the data on the grid below and draw a suitable line. So if we look across the bottom here, we've got 1, 2, 3, 4, 5 spaces, into which we're going to have to fit 22.5 times 10 to the minus 2 meters. Okay, so in other words, we can number these off in fives. Then we'll end up with a suitable scale because it goes up to 25, which is slightly higher than our maximum value here. Okay, up the side, we've got 8 spaces, 1, 2, 3, 4, 5, 6, 7, 8, and we need to accommodate 7 newtons of force. So again, a reasonably easy scale. We can number each of these marks, increasing by 1 each time, so that we've got room for our force data. So at a force of 1 Newton, we get an extension of 7.5. Okay, so we have to reverse those values for this graph, but 7.5 is here, halfway between 5 and 10, and that's with a force of 1 Newton. And then we've got an extension of 10 meters times 10 to the minus 2, and that needs a force of 2 newtons. Okay, so that is here. Then we've got an extension of 12.5 and 3 newtons. 12.5 is there, 3 newtons is there. Then we've jumped in now to 6 newtons with an extension of 20. So there's the 20, there's the 6, and then 7 at 22.5. So 22.5 and 7. And then it asks you to draw a suitable line. So a suitable line in this instance would be a straight line, suggesting that the spring is adhering to Hooke's law. Okay, so state the length of the spring when no force is applied. So here is 0 force, and the length of the spring is 5 times 10 to the minus 2 meters. Okay, so that's the first page done. So that doesn't really involve any higher level material. However, when we move on to this next page, things change slightly. So it says the design company decides to connect 2 of these springs in parallel with each other in the launch mechanism of the model plastic plane. The graph shows how the extension of the spring system changes with force. So as we increase the force up here, then the extension increases along here. The 2-spring system is stretched, and a model plastic plane of mass 55 times 10 to the minus 3 kilograms is attached. A trigger is pressed, which releases one end of the spring system, and the plane is launched. The 2-spring system is stretched to a maximum extent of 15 times 10 to the minus 2 meters. Use the graph and an equation from page 2 to calculate the work done at stretching this spring system. Give an appropriate unit for your answer. Okay, so if we have a look at the syllabus, we'll notice that here we're told that the work done in stretching by finding is found by finding the area under the force extension graph. Okay, so in effect we need to use this equation here. So the equation we need is the one that deals with a force extension graph, okay, which is equivalent really of finding the area under this triangle. Okay, so if we use that equation and put the numbers in that we find on the graph, we should be able to get an answer. So the work done is a half times the force. So if we choose, it doesn't matter which force you choose, but suppose if we choose the maximum force and the maximum extension, that'll get us the most accurate answer. So 16 newtons is the force, and that force of 16 newtons causes an extension of 20 times 10 to the minus 2 meters. Okay, and if we put those values into our calculator, just get rid of that, So we've got 16, which is the force, times 20, which is the extension, times 0.5, which is the value here, half. Okay. Right. Nope. I've just realised I've made an error there because the question specifically asks us to find the work done at 15 times 10 to the minus 2 meters, not 20. Okay, so if I replace that with a 15, and then I also have to replace the force required to create that. So 15 is here. So let's just quickly do that. It'll teach me to rush. Okay, so we need the force. The force is 12. We need to replace that with a 12. Okay, so we do that calculation again. So let's cancel that. So 0.5, which is a half. So 0.5 times 12 times 15. But it's not 15, it's 15 times 10 to the minus 2. Okay, which we're going to get by doing that. Okay, so that's 15 times 10 to the minus 2 gives us 0.9. So 0.9, and because this is work done, and work done is energy, then the units that they're looking for here are joules. Okay, so 0.9 joules of energy. Turn the page over to the last question. Now this is definitely in the realms of higher tier. So it says health and safety guidelines limit the launch velocity of the plastic plane to a maximum of 4 meters per second. Using an equation from page 2 or the syllabus and your answer from B part 1, calculate the launch velocity of this plane when if the mass is 55 times 10 to the minus 3 kilograms and state whether the launch system design meets this safety guideline. So if we have a look over at the syllabus, we'll find that this equation here involves a bit of velocity. Okay, so velocity is mentioned, energy is mentioned. It's called kinetic energy here, but we've just calculated the energy available to be turned into kinetic energy by the spring and the mass. We've been given the mass in the question. Okay, so if we slightly reword that as the energy, okay. Well, actually, we can say KE because the energy in the spring will be converted into kinetic energy as soon as you release it, equals a half mv squared. Okay, now we're interested in velocity because we've been given all these other values in our equation. So in our question, sorry. So we need to rearrange this equation. So to do that, we would get v squared. Okay, so we'd have to have the KE divided by m, and then if you multiply by 2, then that would get rid of the half then. Okay, so it's 2 ke over m. We don't want v squared, we want v. Okay, so we need to take the square root of both sides. So that would be 2 ke over m. Okay, now the ke in this instance is the energy that we calculated in the previous question. Okay, so we've calculated that by pulling the spring back 15 times 10 to the minus 2 meters, then we're giving that spring 0.9 joules of energy. As soon as you release the spring, that 0.9 joules of energy would be transferred into kinetic energy in the plane. Okay, so that there is 0.9. And then our mass is given to us in the question, which is 55 times 10 to the minus 3 kilograms. Okay, that's joules, that's kilograms. So if we put those values into our equation, we would get that V is the square root of 2 times 0.9 divided by 55 times 10 to the minus 3. Okay, so if we use a calculator to calculate that. So let's just get rid of the previous calculations. So 2 times 0.9. And then if we divide that by 55 times 10 to the minus 3. So that's the v squared, but of course we don't want v squared, we want v. So we need to take the square root of that, and that gives us 5.7 meters per second. Okay, so if the launch velocity is 5.7 meters per second, and the safe launch velocity is 4 meters per second, then clearly this exceeds that, and therefore it's not safe. Okay, so this system is unsafe, wouldn't be used. Okay, so you couldn't use that system to build your model aeroplane. Okay, explain why the actual launch velocity is always less than your calculated launch velocity. Well, that's going to be due to losses. Okay, so whenever any device changes one type of energy to another, we end up with losses, usually in the form of heat, but also in the form of sound in this case. Okay, so losses due to heat and sound. So the spring system would get a little warmer and you would hear it, which means that some of the energy that would normally or would preferably turned into kinetic energy of the aeroplane would actually be turned into heat and sound. A student suggests that a maximum momentum value would be more appropriate than stating a maximum velocity restriction for the launch. Explain why this would be an improvement to the health and safety guidelines. Okay, so the momentum is linking the velocity with the mass of the aeroplane. So if you're hit in the face by a very small aeroplane, that's going to be less damage than if you're hit by a large aeroplane, and therefore that would be safer to apply a momentum rather than a velocity. Okay, so safer as momentum as an element mass. If you reduce the momentum value, then both the mass and or the velocity of the aeroplane could be reduced. Okay.